Hello everyone and welcome to this lecture. In this lecture, we are going to continue our regression metrics and KPIs, so let's keep going. So the next KPI that we have is what we call it R squared, or coefficient of determination. So R squared, or coefficient of determination, represents the proportion of variance of the variable y of the output that has been explained by the independent variables in the model, or x, for example. So let's take a look at an example. Let's assume that we wanted to develop a regression model that can govern the relationship between the age, which is my independent variable, and my insurance cost, which is my dependent variable. So we plot all the data points, we draw that straight line, and now the question is, how much variation in the insurance cost has been explained by the variation in age, in my independent variable age, okay? So simply put, if R squared is equals to 80, for example, that means that 80% of the increase in insurance cost is due to an increase in the age of the applicant. That's simply it. So simply put, you go there, you develop your multiple linear regression model or simple linear regression model. You go there, you calculate R squared, and I'm going to show you guys how to calculate R squared, and then it will give you a number. If it's 80%, 20%, or whatever. And based on that number, then you will be able to explain the variation, which is simply the proportional of variations that has occurred in the output as a function of the input. That's all what it is, okay? All right, so basically if R squared is equals to 80, 90, or 100, that's great. That means the model is able to capture the variation in the input. However, if R squared is very small, maybe like 50% or something, that means we need to take action. We need to do something. Maybe we need to increase or add additional independent variables to my model and so on. All right. So R squared represents the proportion of variance of the dependent variable y that has been explained by the independent variables. R squared provides an insight of what we call it the goodness of the fit. How good is my fit? And it gives a measure of how well unseen samples are likely to be predicted by the model through the proportion of explained variance. Simply put, again, if my R squared is again between 0.8, 0.9, or 1, or if it's 80%, 90%, or 100, that's good. That means the more the better. That means you are explaining the variations much better. So maximum R squared value is 1. And simply, if you have a constant model that always predict the expected value of y, regardless of the input, that means you have an R squared equals to 0. That means no matter how much I change, for example, the age, the insurance cost doesn't change. That means age is actually useless. It's a useless independent variable. That means the output is not explained by age at all. There's no even relationship between the two. And that's why R squared, if R squared is very small or equals to 0, that's basically an indication of that. And here is the equation. Again, don't worry about the math of it. I'm going to show you there's a simple function that we're going to use that can calculate all that for us. But R squared simply is 1 minus the summation of, you simply subtract all the data points yi minus yi hat, which is the predictions from the model, and you simply square that up, okay? And then you divide that by yi, which is the actual data points from the output, from the training data, and you subtract that minus the average or the mean. So now, simply put, you are calculating the error or the residual divided by the difference between any data point and the mean of the samples. So that will give you the variations basically, and that will calculate R squared for us. Okay. Again, don't worry about the equation too much or where did it come from, but this is basically the equation. I'm going to show you how to implement that in code. Very simple, very straightforward. Okay. All right. So let's take a look at another regression metric, which is what we call it adjusted R squared, okay? So if R squared equals to 80, for example, as I mentioned, that means 80% of the increase in medical insurance cost is due to the increase in applicant's age. So here, again, if you guys remember, here I have my age, here I have my insurance cost, I plot all the data points, I got my beautiful straight line in here, everything is good, and we're good to go. So let's assume that we wanted to add another useless independent variable. For example, let's assume that we want to add additional variable in here, which is, let's say, the color of the applicant's car, okay, to the z-axis. So we added an additional useless independent variable to my equation, and let's see if that improves r squared, for example, or not. Please note that here we are trying to predict the medical insurance of the applicant. We are not trying to predict the insurance of the car, for example, because the color actually will make a difference in this case. For example, if you have like a red car, for example, in US or Canada, generally speaking, you will find the insurance premium goes up. But this is not the case here because we're primarily focused on the medical insurance. So basically the color of the applicant's car doesn't really matter. We care about the location, we care about the age of the applicant, of the, let's say, smoking habits, of the alcohol intake, stuff like that. Okay, so now r squared, so basically if you increase that, or you add that independent variable, you will find that r squared has increased right now. So r squared becomes, let's say, 85%, for example. And that's one of the major drawbacks when we use only r squared, which is simple r squared. And simply put, if we have a model and we try to increase independent variables, even if they are useless, you will find that r squared actually goes up. So one limitation of r squared is that it increases by adding independent variables to the model, which is simply misleading, since some added variables might be useless with minimal significance, okay? And that's why we have to shift to another metric, which is what we call it adjusted r squared. And adjusted r squared, simply think of this as kind of, like an improvement over r squared that will add a penalty if we make an attempt to add an independent variable that is useless or that does not improve the model. So adjusted r squared, simply put, is a modified version of r squared and takes into account the number of predictors in the model, how many independent variables I took in my model. If useless predictors are added in the model, adjusted r squared will increase. If we use useful predictors, you will find that adjusted r squared will increase, okay? So again, if you add a useless one, you will be penalized for it. And here is the equation. So r squared adjusted equals to 1 minus r squared, which is my regular r squared. And then now we added an additional parameter. Now we added k, which is simply my number of independent variables. And we also added n here, which is the number of samples. So now, simply put, since k is a parameter in there, so if basically the improvement in adding an independent variable does not improve the model, you will be penalized because you are adding k here as a term and you're actually dividing by it. So that's why we call it adjusted r squared, and that's simply adjusted r squared in a nutshell. Okay? All right. So that's all what I have for this lecture. I hope you guys enjoyed it. I hope you guys enjoy the course so far, and please enjoy AWS SageMaker practical course, and I will see you guys in the next lecture.